Hello everyone. Today I recommended a song which is called Under Pressure. Okay, this is an old song released in 1981, I guess. Okay, is talk about something under pressure. So just watch this video, you will see how objects and human beings behave when they are under pressure. Meaning that today we will talk about something related to pressure, stress and strain induced by pressure. Okay, pressure vessels. We will analyze stresses and strain in thin-walled pressure vessels. As we mentioned previously, in this chapter 9 and chapter 10, we will not introduce any new theories anymore. You just need to review the previously learned theories and combine them together to solve some practical problems. Okay, so in this chapter we talk about pressure vessels, and we will just include two types of pressure vessels. One is the spherical shaped pressure vessel, and the other one is a capsule shaped. Okay, capsule shaped pressure vessels. This is our chapter 9, pressure vessels, and in this chapter you will need to use the knowledge in chapter 1 and chapter 8, I believe. Okay, so you will just review this knowledge at the same time. So this will involve the stress definition and calculation in chapter 1. So in chapter 1, just a stress. Okay, just a bearing stress. Just recall the concept and methods to calculate bearing stress. Then we will need to use the knowledge we learned in chapter 8. Okay, basically the Mohr circle. Mohr circle and generalized Hooke's law. Okay. We'll just combine this knowledge to derive equations so that you can use to calculate the stress and the strains in pressure vessels, and then perhaps do some design things, which is based on the pre-known conditions. Okay, the first slide introduce what are thin-walled pressure vessels. Okay, a vessel can be classified as thin-walled if the ratio of the inner radius to the wall thickness is greater than 10. Okay, you can easily find a lot of examples of thin wall pressure vessels in our daily life. Okay, you can see these pictures. I believe you're familiar with all of them, and I believe you have seen some water tanks in Rolla. And when you drive along I-44, you should have seen a lot of other similar tanks with different words on it. Right, Rolla, St. James, Cuba, etc. Okay, just look at the this water tank, the capsule-shaped water tank on this corner, this one. Okay, if you cut it from here, you get a cross section, and the cross section will be a circle. Right, so you have inner diameter R, outer diameter R, then you have this is the T, the thickness. Okay, our definition said if you have R over T larger than 10, so this can be considered as a thin wall. Okay, and if it's a thin wall, then we can do assumption that the description of normal stress in the radial direction is essentially uniform across the vessel wall. That is to say, along the vessel direction, along the radial direction, the distribution of normal stress is just uniform. It's a constant. Okay, we can say that is the sigma A. Okay. And then we will just try to derive equations to calculate the sigma A and further the tau, the maximum shear stress values. Okay, so let's look at the normal stress in spherical pressurized vessel first of all. Here I show a pressurized spherical shaped thin wall vessel. So it has a thin wall and is subjected to an inner pressure P. Okay, inner pressure P. This is the condition. Then to calculate the normal stress, you need to derive the force carried by this wall, and you need to calculate the area of the wall. Right? So to calculate the normal stress, sigma A, we need to know the force P carried by the wall and the area of the wall. Right? So then how to calculate the P? How to calculate the P? We already know that the P, as shown here, right? This vessel is subjected to inner pressure P. Okay, so let's sketch it. Sketch the cross section of it. Okay, get a half circle. So it's subjected to P, inner pressure, right? So your force is here, right? So the force is here to carry to balance this force. This force is generated by this inner pressure P, right? Then how to do this? I need to recall the theory, the simplifications we made in chapter 1 to calculate the bearing stress. Okay, we need area to calculate that bearing stress. Okay, to do that, the P equals pressure times A equivalent. Right? So what is A equivalent? It's a projected area, right? A projected area. So what is that? What is the projected area? In this case, the projected area is just pi r square. Okay? So we can derive that the P equals pressure times pi r square. So we have the P now, and then we need to determine the area of the wall. What is the area of the wall? Cross-section area of the wall. It's a circle, right? So it's a circle, so that is pi r square minus r square. Right. This equation can be extended to pi r plus r times r minus r. Right? So here the r minus r equals t, that is the thickness of the wall. Right? And we know that the r is much larger than t, meaning that this r is not much larger than the inner radius, so they are approximately equal to each other. Okay, so based on these conditions, this equation can be rewritten as pi times 2r times t. Okay, so this will be 2 pi RT. So this is the area, the cross-section area of the wall. Okay, now we can calculate the normal stress in the wall. The normal stress in the wall, that would be sigma A equals P over A wall. The P is pressure pi r square over 2 pi r t. So that would be PR over 2t. Or if you want to use the diameter, that would be PD over 4t. Okay, so those are the equations we derived, which you can use to calculate the normal stress in the wall. Okay, just also keep in mind that you can consider that along all different directions, this normal stress is the same. Okay, as shown here, or along other directions, those are all sigma A. Okay, it's a uniform normal stress. So this is only the equation for normal stress. Then how about the shear stress? How about the shear stress? And how about the maximum shear stress in the thin wall? Okay, here we need to divide it into two scenarios. The first scenario is on the outer surface, and the second one in the inner surface. Okay, since they are different, the outer surface and inner surface will be different because on the outer surface, this wall is not subjected to any pressure. Right? But in the inner surface, it's subjected to a pressure of P. Right? So this is different. So let's look at the outer surface first of all. Okay, on the outer surface, you can cut a three-dimensional stress element, and the three components of it will be sigma A, and 0, since it's not subjected to any pressure. It's along the radial direction. Okay, so those are the three components: sigma A, and 0. Okay, so based on these three components, we can draw more circles. We can draw 3 more circles, right? Just recall the process we used to derive the 3D Mohr circle. Okay, then we divided into 3 cases, colored by green, red, and blue, respectively. Okay, look at the case 1 first. To draw the Mohr circle, we need to get a coordinate system first. Then look at case 1. Let's use the green color. Okay, case 1. In case 1, you have here, this is sigma A, and this is also sigma A, and tau equals 0. Okay, you just find the 2 point. Sigma A 0 is the first point. Let's see, sigma A 0 is the first point. And the second point is also sigma A. Sigma A is 0. Okay, it's 2 points together. Okay, what does that mean? How can you draw a Mohr circle based on only 1 point? Okay, so in this case, the Mohr circle is just a point. Okay, it's just a point. This is the Mohr circle in case 1. Then what is the maximum shear stress? It's a point. Okay, so maximum shear stress in plane is 0. Okay. Then how about the case 2? In case 2, you have here, red colored here, you have sigma A 0, and on the other direction, 0, 0. Okay, so this is the first point, and this is the second point. Connect them together, you get the radius. You get the diameter, right? Then you can draw the Mohr circle. Okay, you get this Mohr circle. Then what is the tau max in plane? It's the R, right? So here is the tau max. What is that? It's this equals the radius, right? The radius equals sigma A over 2, right? It's just a PR over 2T over 2. right? So that will be PR over 4T. So this is the PR over 4T. So this is the in-plane maximum shear stress in case 2. Okay, PR over 4T. Then how about the third case? In the third case, you have along this direction, you have sigma A. Along the other direction, it's 0. Okay, so this is exactly the same as the second case. Okay, so if you want to draw the Mohr circle, you get the same Mohr circle as case 2. Then the in-plane maximum shear stress will be the same. This will be PR over 4T2. Then what is the tau max, the absolute maximum shear stress? That is the maximum number in these 3 results. Okay, so what is that? That is just a PR over 4T. Okay, so this is the equation we derived for the outer surface. For the outer surface, the absolute maximum shear stress on the outer surface. Then how about the inner surface? What is the difference? As we just mentioned earlier, the difference will be that on the inner surface, you have a pressure along the radial direction. Okay, along the radial direction, that is T. Okay, then along the other 2 directions, you have the same as the outer surface, the sigma A PR over 2T, sigma A PR over 2T. Since we assumed that the distribution of normal stress along the radial direction across the thin wall is uniform, right? So these 2 components will be the same. Just the third component will become P, not 0. But is that positive P or negative P? The inner pressure will compress the inner wall. Okay, so that is negative P. So that is to say, you will have the 3 components of a 3D stress element on the inner surface. That is sigma A, and negative P. Okay, again, we can divide this scenario into 3 cases. The green colored plane, red colored plane, and the blue colored plane. Okay, now let's look at the case 1 first. Okay, this is case 1. Let's draw the Mohr circle. In case 1, you have the first point, PR over 2T 0. Second point, PR over 2T 0. Again, it's just a point. Okay, this is the Mohr circle. So the tau max equals 0. And in the second case, okay, you have sigma A along this direction and negative P along the other direction. Okay, so the first point will be PR over 2T here. The second point will not be 0, okay, not be the origin. It will be negative P, negative P0. Okay, connect these 2 points at the diameter to draw the Mohr circle. So you get a Mohr circle as this. Okay. Then what is the radius? This is the tau max. Okay. Then let's see what is the diameter first of all. Okay, the diameter will be like here is PR over 2T 0, and here is a negative P. Okay, the diameter, of course, obviously that will be PR over 2T minus negative P, okay, or plus P. This is the diameter. Then how about radius? Radius will be just d over 2, right? It's a PR over 4t plus p over 2. Okay, so this will be the tau max. Okay, the tau max just equals PR over 4t plus p over 2. Okay, so here our results will be PR over 4t plus p over 2. This is the in-plane maximum shear stress in case 2. Now how about case 3? In case 3, you have sigma A negative p is exactly the same as case 2. Okay, if you want to draw the Mohr circle, you get exactly the same Mohr circle. So the maximum in-plane shear stress will be the same. Okay, will be PR over 4t plus p over 2. Then our question is, what is the absolute maximum shear stress? That will be the largest value in the 3 results. So obviously that is just PR over 4t plus p over 2. Okay, so you can see that we have these 2 different cases on the inner surface and outer surface. Okay, in the outer surface, you have the stress along the radial direction 0. So the absolute maximum shear stress is just a PR over 4t. Right, it's half of the normal stress. And on the inner surface, because of the pressure, right, this absolute maximum shear stress will be a little larger. It's a PR over 4t, or half of the normal stress, plus half of the pressure. And this slide summarizes these equations we just derived, so that you can calculate the normal stress and shear stress, or maximum values of normal stress and shear stresses, so you can compare them with the strengths to check if your design are safe. Okay, or based on the preconditions, based on the given allowable stress values, to select the sides to determine the diameters or the thickness of the wall. Okay, this is what you can do based on these 3 equations. And the 4th equation is used for strain calculation. So you can see that this is a normal strain on the wall. Okay, this is derived from the generalized Hooke's law 2D case. Right? So when you have a 2D element, I have sigma A, also sigma A here. So what is the strain along any one of those 2 directions? Okay, obviously based on the 2D generalized Hooke's law, the sigma A is calculated as 1 over E times the sigma A minus nu sigma A. Okay, here the sigma A equals PD over 4T. Right? In these 3 equations, the use D, not R. Okay, just got a PD over 4T. So you just get this in here, so you will be able to get this equation. So this is how we derived this equation, the 4th equation.